This is the video recording for Algebra 2, Unit 5 on polynomial functions. So to bring out the overview for this entire unit here, I can have you watch this on your own just for the sake of time. But basically, we're going to learn about polynomial functions, what they are, how they're graphed, how to manipulate them, and again, all about those special things we call polynomial functions. All right. So in the overview here, a polynomial is a number, it is a variable, it is an expression, but not everything is a polynomial, all right? And we've spent a lot of time working with polynomials, but we maybe haven't known it the whole time, or we haven't really expressed it explicitly, all right? But we're going to introduce ourselves in this first unit here. It is an overview of the basics here, so figuring out what they are, how to manipulate them, and again, kind of glossing over some of those general introduction things here. All right, so if we look at this here, we've learned about two expressions so far, linear and quadratic, and both of these functions are polynomials, all right, but not everything is a polynomial as we talked about. Okay, so polynomials have this function where it's a n x to the n plus an minus 1, x to the n minus 1, right, so on and so forth, until we only have a here, right? And a, as we've talked about, right, and even these earlier a's, those are your numbers, right? X is your variable, and then n can also be a number. And what this is saying is you have some degree here, plus a smaller degree, plus a smaller degree, all the way down until we have just a constant by itself. All right, so if we look here to scroll over this a x to the n term, all right, so a is a coefficient, and it's the coefficient by which, it's a constant, right, the number by which the variable is multiplied. All right, x is our variable, it's just our unknown quantity, and then n is our power of the term, right? It's also a whole number. And n, so we could say this is x to the nth power, x to the nth power. All right. Moving forward here, there are, like I said, there's coefficients, variables, and power for each term in the polynomial, all right? And a polynomial is arranged from highest degree to lowest degree when it's in our standard form, right? We talked a whole lot about the value of putting everything in standard form, and you can see the standard form for an algebraic expression down here. And basically what happens is you start with the highest degree, right? And what does degree mean, right? It's to the power at which it's raised. So this x to the fifth here is raised to the fifth power, so it has a degree of 5. Okay, this term has a degree of 3, this term has a degree of 2, this term has a degree of 1, and this term technically has a degree of 0, okay, because x to the 0 is just 1, right? Any number to the power of 0 is 1. All right, and you can see here that we are missing like an x to the fourth term, right? So it doesn't always have to have every term in order to be considered a polynomial expression here, all right? But if we spend a little time here looking, again, it's arranged from highest order to smallest order, all right? And the polynomial, again, this is the degree of its leading term, right? So this entire polynomial is a fifth degree polynomial based on the fact that we have a fifth degree term is the highest term. All right, so this is a fifth degree polynomial. Again, the leading term has the highest power, and this one has a coefficient of 1 and a power of 5. All right, if we go here, this term has a coefficient of 2, a power of 2, and like we said here, just to clarify, this is technically 6 times x to the 0th power, but any number to the 0th power is 1, so it's like saying 6 times 1, so we say it is a constant, right? It's the term without the x variable. Okay, moving forward here. An expression is a polynomial if and only if it meets all of the following conditions. So first condition is there's no fractions that contain variables in the denominator. So right here is not a polynomial because it has a fraction in the denominator. All right. There can only be whole numbers. For exponents, so it can't be fractions or negative exponents. So right here we have x to the negative fifth. So this one is not a polynomial as well. All right, there can be no radical expressions that contain variables. Well, here's a radical expression, and that would be fine if it was by itself, but it has this x variable, so this one is not a polynomial. Right, and then finally, all coefficients are real. Okay, they may be fractions, radicals, or irrational numbers, but they cannot be imaginary numbers, so they have to be all real coefficients. So finally, the last one there that's left over, that blue one, is a polynomial because it follows all of the above rules. All right. Moving forward here, we can combine our functions, and we've already learned a whole lot about these here, so I don't want to spend too long, but we can combine functions in the same way we've done with the previous functions. We can add, we can subtract, we can multiply, we can do all of that things. So if we look here at this problem, x squared plus 3x minus 1 plus the quantity of 4x squared plus 2x plus 5. Okay, so since this is a positive number, right, we're just going to combine like terms and add them together. So if we look here, combining those like terms, there's nothing different to do. All right, so we can simplify to this final version here. All right. Now, when we're doing subtraction, again, we've got to distribute that negative charge throughout the entire quantity that's getting subtracted, right? So you can show this with a factor of -1, right? I don't ever really show it like this, but this is a good way of thinking about it if you're struggling with carrying that negative sign, right? So basically what you're saying is you're carrying that -1 sign through both of those terms. So this -2 turns to a +2, right? Once we've carried that through, we can just then collect our like terms per usual, right? Add them together, and then we can simplify to get our final expression there. All right, so nothing we haven't seen before, just reiterating a lot of things. Now, we talked about naming things, all right? So a binomial is a polynomial with two terms. Again, bi meaning two. It's the abbreviation for two, all right? So a binomial is a polynomial with two terms, okay? And we've been dealing a lot with binomials, especially with our linear equations, right? Our y equals mx plus b or ax plus b. All right, and just to reiterate here, if you've got a monomial, which is what we call a one factor, and we've got this binomial, we can carry out through or distribute, right, that a to both of the properties in there, okay? So you can also do this by multiplying two binomials, all right? And bear with me here, right? So you can take the two binomials and multiply. So you've got this first one multiplied by, this whole term multiplied by this first term, plus, since that's a plus sign there, plus this guy multiplied by the second term. We can then distribute. Okay, we distribute, we collect like terms, and we simplify. All right. Another way of doing this that we've been using a lot more than the that method is our FOIL method, right? So our first, we multiply by our first two terms, multiply by our outer two terms, multiply by our inner two terms, and then finally our last two terms, okay? And so that's the one that we've been using a lot, and that I hope we're all more comfortable with. But you can use any of the methods. They all end up with the same answer, all right? Then once we get this, obviously we collect like terms and we simplify. However, there are some special cases of FOIL that make things a little bit easier, right? Just some things to identify. So this first special case here is if we have a plus b multiplied by a minus b, right? And we've talked a lot about this being our perfect square trinomials, right? Or our or are completing the square or factoring squared, right? So we've seen a lot of this in different forms here. So looking at this first one here, okay, an example might be 3 plus 2 multiplied by 3 minus 2. It's going to end up with a squared minus b squared. All right, and again, we can always go through the full FOIL process, right? I'm never going to get mad for going through the full FOIL process, but if you can remember these shortcuts, it might shave a couple seconds off of your time or help you recognize some patterns here. All right. Special case number 2 is if we have a plus b squared. What that means is you've got a plus b multiplied by a plus b. Again, when we FOIL that guy out, we're going to end up with our a squared plus 2ab plus b squared, right? And we've definitely seen this here before. Okay, we've definitely seen this here before. All right, and warning, okay, a plus b quantity squared is not the same as a plus b by itself squared. So again, parentheses make a huge difference and can change your factors. All right, special case 3 is if you have a minus b and that quantity is squared. So again, you have a minus b times by a minus b. We FOIL that guy out again. We are left with basically the same thing, except for now instead of adding our 2ab, we are subtracting our 2ab. And again, same warning there. All right, so special cases, they are also sometimes known as the polynomial identities. All right, polynomial identities, or we've talked about them a lot with other things there. Okay. So what about polynomials that are not binomials, right? So maybe a little bit more difficult, maybe not being able to use FOIL as easily if you're not as comfortable with that. So you could still use the distributive property there, right? So multiplying this entire thing by the first term plus the entire thing multiplied by the second term. So again, then distributing, perfect, simplifying, right? Collecting like terms and simplifying. Right, there is another way of looking at this here, and bear with me because it does make a little bit more sense with something that's not as easy as just two binomials, right? But if we multiply our polynomials, you can do this as we would do like just multiplying factors itself. So first off here, we multiply 2 by the top quantity, okay? Then we're going to multiply x by the top quantity. And you notice here we shift over away from the 6 here because we're dealing with our x factors. All right, then we just add vertically down. So 6 and 4 plus 3 is 7x, and then 2x squared. All right, so that's a way of doing that. And where that would really come in handy is something like this. If you have a 3 by 3, right, you can definitely do something like this. So multiplying everything by 1, moving up to the next guy, multiplying everything by 4x, again, shifting your answers over by 1, and then multiplying everything by 3x squared. Okay, adding them all up, and then we get our final expression there. Okay, and finally, lastly here, we can divide polynomials, all right? So I will say that throughout this unit, we will work a lot more on dividing polynomials. So if this is a little bit confusing, by all means, take a breather, relax, because it's going to get explained in a lot more details. Okay, so when we're just introducing here in this first unit, we're going to talk in generals about how this relates to numbers, and we'll provide some examples here. So if we zoom in so we can watch this video here.
First, review some words that describe the parts of a division problem. In this problem, 23 is the dividend, 5 is the divisor, 4 is the quotient, 3 is the remainder. The method for dividing polynomials is a lot like the one you use for dividing numbers. You even use the same words to describe the parts of a polynomial division problem.
Okay, so again, knowing those words are going to be super, super helpful here because they're going to get used throughout the further units here. So again, they're going to be explained in more details. But again, knowing dividend, divisor, quotient, remainder. All right, and they showed it like this because remember, you have your quotient, which is your raw answer, and then you add whatever your remainder is divided by your original divisor. Sorry about that, and we'll provide more examples moving forward here. All right. So again, similar to integers, here is more on the remainder and what that looks like for polynomials.
Take a look at the problem on the right. 23 divided by 5 is equal to 4, with remainder 3.
Okay, so again, 3 divided by your original divisor.
You can also get remainders when you divide polynomials. At any point during long division, if the degree of the difference is less than the degree of the divisor, then the divisor will not divide evenly, and you will have finished the problem. Take a look at an example.
Okay, so, you look at the first one here. Okay, we've got 3x squared, right? And that will go into, or x will go into 3x squared 3x times. Okay, so then you multiply 3x by that quantity. Okay, then you subtract everything and get negative 2x. Okay, so then you got to fit how many times does x go into negative 2x? Okay, it goes in negative 2 times. And then you multiply the entire quantity, and we are left with a remainder of negative 1 there. Okay, and there you go. It says the degree of the difference is less than the degree of the divisor, right? So the degree of the divisor here, right there, that's x to the power of 1, right? That's x to the power of 1. But this guy here, remember, this is x to the power of 0. So this is less than this guy, so you are finished with the problem. We can't put x into negative 1, right? So we're done with this problem here. All right, and right there, perfect. In case you're worried about it, you will spend more time on this idea in a later lesson, so do not freak out about it if this is a really quick overview for you. Okay, so then closing operations here. Okay, you can do the same thing for polynomials that you can with integers, like whole numbers. All right, but the key here is what happens with division. What happens with division? All right, so when we're looking at this here, okay, you end up with your final answers here, okay, and we end up with our whole set of integers when we're doing our problem. But when we look here with division, right, 3 does not go into 25 evenly. It goes in 8 1/3 times. So when you're looking at this here, 8 1/3 is not an integer, right? It's not a whole number. Okay, same thing as if when we're dividing here, if we end up with this remainder, right? And here's an example of what it would look like, 1 over x plus 1, our original divisor. Okay, this violates one of our rules, right? Where you can't have any x variable in the denominator. So this is no longer a polynomial. All right. So then here, answering this question, integers and polymers are not closed systems under division, right? By that it means it can go from being a polynomial to not a polynomial if you divide and you have a remainder. Okay. By that I mean, again, you can't start off with an x variable on the bottom, right? And if you divide and you get rid of all the x variables, you can end up with a polynomial, right? So if this was just 2x plus 1, okay, this one wouldn't violate. So we would start off as not a polynomial, and we would turn into a polynomial through the process of division. However, when we have this remainder here, we still remain not a polynomial. All right. Again, talking about common factors. So the first common factor that we actually talked about was pulling a value out of every number, right? So if everything was multiplied by 2, we could pull 2 out, and that would be a common factor. All right. Another way of doing this is we've done a ton with looking at factoring quadratics, right? Where we can figure out what those two are, then we can set them equal to 0, and we can solve for the answers, right? So we spent a lot of time dealing with quadratic problems. Okay, and it's going to be the same thing here, except for you might have things that are a little bit more complicated or a little bit more than just x squared. All right, and again, reminding you here, the difference between these two is there's this a constant here. So now you have to have this new r and s. So when we factor, again, it's rx plus or minus p multiplied by sx plus or minus q. All right, so again, that's the only thing you have. It's a little bit different, and something to think about there. All right. Now, if we continue with the polynomials here, again, a polynomial is an expression that can be written in the following form. All right. Polynomials as closed systems, all right? Like integers, polymers are closed systems under addition, subtraction, and multiplication. That means if you add, subtract, or multiply, the result's going to be another polynomial. However, under division, polynomials are not closed systems, right? Because the resulting, by dividing one of the polynomials, it may or may not result in another polynomial. Right, so individually they can be polynomials. When you put them together, the original expression is then not a polynomial, right? So it may or may not be a polynomial. All right, so here's some questions that you can practice and try on your own. And then again here, just being able to put this in order of greatest term to least term. So right here, you want to make sure that you start off with the highest term polynomial, so that x7. Right, then next we want to have the next highest term, which is a 5 here, right? So it's going to go 7 to the 5th, to the 4th, to the 3rd, right? And then this one is to the 0th. So your answer here should be B. All right. When we do this one here, remember, you've got to carry that negative sign throughout the entire thing. So you're going to have x to the 7th. It's going to be minus 4x to the power of 6 minus 2x to the power of 6. This is going to be a plus 2x to the 6th. So all of those are the same so far. Then I'm going to have a minus 3x to the 5th. all right, minus 3x to the fifth. So we've gotten rid of that middle term, all right? And then I've got a negative x squared minus a x squared as well. So that's going to be minus 2x squared, right? So right there then I have my answer. My answer is A. All right. Using the FOIL method, first, outer, inner, last. You should be able to do that one. We've done a ton. Okay, and then what's the product of the polynomials in the box, right? So again, reminding ourselves that this is where we multiply the bottom, the first term on the bottom by every term on top, right? And then we multiply the next term by everything on top and we add them all together. All right. So looking here at our study guide, okay, so you can write a definition for the word power. Okay, it's also called an exponent, right? It's what you multiply, or the number of times you multiply the base number by itself. So 2 to the power of 4 means you're multiplying 2 by itself 4 times. So 2 times 2 times 2 times 2. All right, so A here again is a coefficient, X is our variable, and then N is our power. All right, so then a polynomial is in its standard form when all the terms are written from lowest to highest, right? So this guy here is our leading term, and this ending guy here is our constant. Okay, so then when we look at our rule and our examples, okay, there are 3 of the good rules here. So if a term doesn't have a number in front of the variable, then the coefficient of that term is a 1. All right, so for example here, the coefficient of x is 1. The coefficient of a number, the coefficient of a constant term is the constant number itself, right? So technically this is 3x to the 0th, okay? And the constant then is 3. And that brings us to rule 3. If a power is missing, then the coefficient of that power is 0. So technically here, there is no x squared term, right? So that would mean that is 0x squared. Okay, so then these were the 4 rules that we talked about here. So no variable in the denominator, so this is not okay, but this guy is, because again, you can't have the variable there. Only a whole number exponent, so this has to be x to the 4th or x to the 1st. It cannot be to the 1/4. There can be no variables in the radicals. All right, so this quantity can be squared. It can be times 3. It just can't be underneath the radical. Also, you could put, like this one here, only real coefficients. So you could put a square root of -5 here, or -4 for this one. That can be under the square root. But for this one, this is not true because it's -4, right? -4 would give us an imaginary number, so it has to be the square root of 4. Okay? So for doing these steps here, okay, you're going to remove the parentheses, collect like terms, and simplify. Hopefully simple here. All right, adding polynomials vertically, simplify the sum, add the polynomials, arrange vertically, and then fill in the missing terms. Okay, so the order of that would be, we need to arrange the problem vertically, so make sure that they're in order, okay? Then we need to fill in any missing terms using 0 coefficients. So for example here, if I am missing an x to the 3rd, right, it's just 0x to the 3rd, okay? Then once I've done that and filled in those 0 coefficients, I'm going to add them together and simplify the sums. All right, and a really good example I'm pointing out right here is down here where I have 0x squared, okay? So that's an example of just filling in with the missing term there by having it be a 0, okay? Subtracting the polynomials vertically, okay, same thing. Make sure the polynomials are written in descending order, okay? Write them vertically, replace any with 0 coefficients, multiply everything on the bottom by a -1, and then you just add the polynomials together. All right. When we're using the distributive property, okay, variables A, B, and C. So this first quantity here is A, then we're saying that this second one is B, and this one is C. So when I use my distributive property, I multiply my A quantity by B and my A quantity by C. All right, and then repeat the steps again for those smaller products. So My A value for this one would be my 2x multiplied by x multiplied by 3. Same thing here. I've got 4 multiplied by x multiplied by 3. And then I can combine them vertically. Or what you can do instead, if that doesn't work out for you, or you know it's impossible with that one, you can do the FOIL method. So first, outer, inner, last. All right. And then when we're dividing the polynomials, we'll spend a lot more time on this one, I promise. Okay, but they're separating a total into groups, right? That's the goal, is we're trying to separate it into groups. So when we look at the practice here, so you're doing it based on long division here, okay? So again, you ask yourself, how many times does x fit into 2x squared? Well, that would be 2x times. Then you multiply that quantity, right? Then you subtract everything, okay? Bring down the 3, and then again, ask yourself, how many times does x fit into x? Well, that would be a 1, so it's plus 1. And then this one here has no remainder, okay? The remainder is 0. And what it's saying by check is check by just multiplying them back together, right? If you multiply them out, then you should get the original expression. All right. And if we look here at number 2, we can do the same thing, but now they showed it as r, which means remainder 15, or another way you could say that would be 15 over x over 2, right? Our original dividend. All right. And in the way that they checked it, they just multiplied the two binomials together, and then at the end they added in that remainder. So they just did the plus 15 right there as a remainder. Okay, so you can definitely do that to check. All right. So that's the 5.1 study. And again, looking here, you have this 5.13 quiz. Skip the practice or use that as extra credit if you would like it. And looking at our checkup here. All right, looking at our checkup, you're going to have a lot of the same type of problems that you saw earlier. Again, except for, to start off here, so listing the following as polynomials, not polynomials, right? And then classifying them as monomial, which means 1, binomial, which means 2, or trinomial, which means 3. And then the degree is based on the highest power that you have for that exponent. So if we look here, okay, let's look at one that's not. All right, so we look here first. This is not a polynomial because you've got the square root of x, right? So that's not a polynomial. All right, this one is also not a polynomial because you have to the power of fractions, and that violates one of our rules. Okay, if we look here though, this one is, we have all real numbers. There's nothing violating our rules. So when it's written in this standard form here, it is a polynomial, okay, and it's got 1, 2, 3 terms, so it's a trinomial, and its degree is 2 because it's to the power of 2. All right, this next one here, you got to be really careful. That is only the square root of 2. It's not the whole y to the third also. So for this one here, it is a polynomial. It is a binomial because there's only 2 terms, and then the highest degree is 4. So it is a 4th degree polynomial there. All right. Then it's saying state why or why not it is a answer the questions. And then this one says, why does the following statement show that polynomials are not closed under division? And the reason that one is because if we take 2 polynomials, right, these are 2 polynomials, and we carry out the division process, this results in it not being a polynomial. All right. And then here, multiplication, right? Making sure we can do the multiplication process for these guys under the different terms. So if you want to do FOIL, if you want to stack them on top, any of that, right? We should be able to do that. And notice here, they don't really focus a lot on division because, like I said, I promise we'll go through that more in a later unit. All right, again, go through this, look at your answers, and you only have that one quiz that you need to complete for this unit.